Hi, this is Tzvi Rosen. Today we're going to talk about volumes more generally, as well as disks and washers, which are tools that we use in calculus to compute volume. First off, what do we mean when we say volume, and how does it fit together with the other notions of length and area? Well, when we say the length of a line segment, what we're really saying is how many units, like a standard unit, fit into that line segment. So in this example, this drawing on the right, we see a line segment, which when we line up units next to it, we see that 2.5 can fit in. Okay, so that's what we mean by length. We have some standard unit, and we're comparing our line segment to that unit and seeing how many of those units will fit in. When we talk about area of a region, we make a similar calculation. We try to fit square units, so that's a square whose one edge is a unit and the other edge is also a unit, and we try to see how much of those square units we can fit into the region in question. In this case, we have a triangle, and we fit a bunch of square units in. Obviously, a unit like this is not inside of the triangle, but by adding up all of the fractions of square units that we get, we can estimate the area of the region. Okay, and similar to all of that, when we are looking to compute the volume of a solid, where a solid is kind of like a region but in 3 dimensions, the question of volume there is also how many cubic units fit in the region. And the cube here, it's got all of its 3 side lengths are 1 unit each. Okay, and that computation gives us a sense for what volume will be. And so that's what we're talking about when we talk about volume. But how do we compute this more precisely? Okay, one class of examples that allows us to compute this quite precisely is cylinders. A cylinder is a shape formed by giving height to some 2-dimensional region. For example, from a square, we get a cube. So here's a square sitting in a 2-dimensional plane. Oops, wow, that's very much not a square. Let's try this again. Okay, this is sitting in a 2-dimensional plane, and we allow ourselves to have 1 unit of height, and that gives us this cube. Okay, and this is a cylinder. The cube is really a cylinder over a square. Okay, if instead of a square we started with the circle, okay, what we get when we follow the edges up, giving this circle some height, this is what we're accustomed to calling a cylinder. Looks a little bit like what a tin can is shaped like. As for this final example, if instead of a rectangle or a circle, we have a triangle in the plane, what we get sticking up out of the plane when we give this some height is called a triangular prism. Okay. And in each of these examples, the area of the slice, so we started with something in the plane, and if you notice, if you slice it across anywhere along that height, you're going to get that same shape. So that's called a cross-section. And the rule for these cylinders is the volume of a cylinder with cross-sectional area A is V equals A times H. Okay, so this is our height, and the area of this region is A. Then the volume of the resulting cylinder is V equals A times H. Okay, and the same for the other examples. Okay, so cylinders, these are examples that make intuitive sense. If you start with an area and then you just stretch it out in the next dimension, just multiply by the height. What happens when the solid is not a cylinder? And this is not particularly difficult to imagine. If you think about the classic three-dimensional things, well, a ball is a good example. Okay, this doesn't stay constant when you take cross sections, right? If I look at a cross section over here, I get kind of a small circle. Should probably touch the edge. But if I take the cross section up here, it's a much bigger circle. Okay, and if I take the cross section up here, it's a teeny tiny circle. So this is not a cylinder by any stretch. But our idea is, in the spirit of integral calculus, we're going to approximate the region as a sum of cylinders. Then we take the limit as the cylinders get smaller and smaller. Okay, and in this picture, what that would look like is we have a bunch of these tin cans, and we try to approximate the region in terms of the sum of these tin can volumes. Apologize if this is not super visible. But as you let those cylinders get smaller and smaller, you're going to come closer and closer to representing the true volume. And that's what's given in this formula. We're taking the limit of the cross-sectional area times the thickness. And then as you take the limit where that thickness goes to 0, what you're doing is approaching this integral, which is the integral from h min to h max. Okay, we can think of this as height or some other coordinate along the volume. And this is cross-sectional area. At position h. Okay. So let's do an example where we use that integral formulation. We're asked to compute the volume of a square pyramid with base length s and height h. Okay, so let's remember what a square pyramid looks like. A pyramid is something that has a point on top and has some shape on the bottom. In this case, because it's a square pyramid, it has a square on the bottom. Okay, I'm drawing it. It looks a little bit like a parallelogram, but that's just to get some perspective. Okay, so every side of this will have length s, and then we connect all of these corners to this central point up above, and that's sitting above a central point here. And let's let that be our h. Okay? So now we want to think about what's the cross-sectional area when you slice it in the horizontal direction. Okay? So what does this look like? You can probably convince yourself pretty quickly that the cross sections are all squares. Squares with side length, and this is the tricky part. Let's leave it blank for now. We need to figure out what this side length is, because we know to start it's going to be s, right? Because we're given that the base of the square pyramid has side length s, and at the height, the highest point, the square becomes a point, so it's going to have side length 0. Okay, so we know. So if we're expressing that in terms of h, we know that s of 0 equals s. Okay, and then maybe we should give this a different name, because we already have s in here. So let's call this L. So L of 0 equals s, and L of h equals 0. So what that means, because this is, you can see that this is decreasing linearly from s to 0. So we're going to want a linear function which takes the value s at input 0 and it takes the value 0 at input h. Okay, so that one possible function like that will be L of x equals minus, how should we do this? Let's make this minus s over h times x plus s. Okay. I'm just going to clean this up a bit. Minus s over h times x plus s. And if you plug in L of 0, you see the first term goes to 0. So that's s, which is what we want. And if we plug in h, we get minus s plus s, which is 0, also what we want. Okay? So now we need to express this. We have the cross-sectional area. We know the side length of a cross section, and the cross-sectional area. So the area of a cross section will be just given by s squared, right? But because the base length is s, so let's make this L of x squared. Okay, so to get the volume, we're taking the integral from the smallest x value, which is going to be 0, up to the largest x value, which is going to be h, of the cross-sectional area, which is L of x squared dx. Okay, now here we're going to plug in our value for L of x that we computed. This is 0 to h, and we have minus s over h times x plus s squared dx. And that gives us, again, an integral from 0 to h. Taking the first term is s squared over h squared x squared minus 2s squared over h x plus s squared dx. And we get, term by term, we have s squared over h squared x cubed over 3 from 0 to h minus 2s squared over h x squared over 2 from 0 to h plus s squared x from 0 to h. Okay, and let's grab that. And we'll take this onto the next page to finish up the computation. Okay. And we have h over here. So we're going to get s squared h cubed over h squared times 3. Okay, and the 0 term vanishes. Minus the 2's cancel here, so we get s squared h squared over h plus s squared h. Okay, now we should simplify. We have s squared h over 3. Okay, a couple of factors of h cancel there. Minus s squared h plus s squared h. So we should get s squared h over 3 as our answer for the volume of the square pyramid. Okay, so this is an example of just using the definition of volume as the sum of all of these small cylinders. Okay, and we were able to use that to find an explicit formula for the volume of a square pyramid. Okay, now we're going to talk about a solid of revolution. And this is going to be the main object that we're going to compute volumes of in this section as well as the next section. And here's what you need for a solid of revolution. You start with a region in the plane, and you also need a line in the plane to revolve around. Okay, so for instance, here's an example. Sketch the solid of revolution obtained by rotating the region bounded by y equals sine x plus 2, x equals 0, x equals pi, and y equals 0 around the line y equals 0. Okay, so let's start by just drawing this. Let's draw some axes. So we need to go from x equals 0 to x equals pi, and y equals, and it needs to involve y equals 0. So let's get some axes here. We'll make this pi, which means this is pi over 2. This will be pi over 4. Okay, and notice that y equals sine x plus 2, so when sine takes its maximum, y will be as large as 3. So we want to make sure we get up to 3 here. Okay, and now we can draw our curve. Or we can draw the region, I should say. So we have y equals sine x plus 2. So sine starts out at 0. Okay, then it goes up to 1 over here. And at pi, it goes back down to 0. Okay. So we get a curve that looks like this. Okay. Then if we're looking at x equals 0, so that's here, and x equals pi is over here, and y equals 0 is here. So this is our region, the thing we see outlined in blue. And now this is how we get a solid of revolution. We just imagine that there's another axis pointing out at us from the screen, and we're letting the region kind of swing towards us and all the way around. So at each point here, we're going to get a circle pointing, oops. We're going to get a circle and we can even add some dotted lines in here to make this a little bit, to make it clearer that part of it is behind, is kind of in back, and part of it is more towards us. Okay, and we can show that this has a bottom outline here. And we can even draw some cross lines here if we want. Okay, so this is how we get a solid of revolution. This picture might not quite do it for you, so I thought we would look at this rendering software, Blender. So this is a curve sitting in the plane, and this is what we would get if we rotated it around. So if we're thinking about the region which sits underneath here, so think about from the red line up to this curve, then the associated solid of revolution would look kind of like this. So you get a circle at each point along that curve, and we can kind of turn this around and see what it looks like from different perspectives. So this looks hollow because just the way the software is. In terms, if we want it to be a solid, you would imagine this all filled in. But this lets us get a better picture of what this looks like. Okay, from this perspective, you can see everything is a circle, because, so this is looking just at the x direction. So this is as if we're looking along the axis of rotation, and everything is kind of going around it. So everything is a circle from that perspective. But going back to the perspective we started with, we see that we have the top curve, the curve that defined the top of the region up on top here, and then its reflection down here. And if you're interested in visualizations like this, you can just Google visualization solids of revolution, and you should be able to find a lot of really interesting visualizations. Okay, but let's move along in these slides. So the method of disks, which is how to compute the volume of a solid of rotation, a solid of revolution, is when the region sits up against the line of rotation, like in this example that we just saw, where the bottom of the region was also the axis of rotation, which we were spinning around. All of the cross sections are circular disks. Okay, and the infinitesimal volume of a disk at position H is given by dV, that's the infinitesimal volume, is equal to the cross-sectional area times an infinitesimal thickness. And that cross-sectional area, because it's a disk, is just pi r squared dH, again times that infinitesimal thickness. And here r of h is the distance from the axis of rotation to the edge of the region at position H. So you go as far as high up as the disk goes, and dH is the infinitesimal thickness along the line of rotation. Okay. In the particular case that this is the x-axis, that the x-axis is the line of rotation, and the region is bounded by a curve y equals f of x from x min to x max, and we saw an example like that above, the formula becomes dV equals pi times f of x squared dx. And so the total volume of the solid of revolution is obtained by integrating the integral from x min to x max of pi f of x squared dx. Okay, and just to give you a brief picture, so here we have our x-axis and some region along here. Okay, so this value here, y equals f of x, is defining that top curve. And then this will give us some x min and x max. That tells us where to start taking our integral and where to stop. So this will be x min. This is x max. And this tells us the volume of the solid that you get when you revolve around here. Okay. All right. And we get a very similar picture with the if you're rotating around the y-axis, just everything is in terms of a function of y. And I'll draw a quick illustration of that. So here you have some function x equals g of y, and here's a y min and a y max. Okay, then by the same token, you just imagine this spinning around. Okay, and you get the volume of this by taking this integral. Let's do an example. Let R be the region bounded by 4 minus x squared and the x-axis. Compute the volume of the solid obtained by revolving R around the x-axis. So let's first draw the situation that we're looking at. So here's our axes. And we have the region 4 minus x squared and the x-axis. So four minus x squared is a parabola which sits here. Okay, but because I want it to be bounded by this curve and the x-axis, I'm just going to stop as soon as I hit the x-axis. Now this is my region. Okay. So I'm going to be rotating this around the x-axis, which means things are looking like this. Okay. If I want to think about an individual cross-section here, I have a disk whose radius is given by the value at the curve. So that's the integral from x min to x max of pi times f of x squared dx. And this uses the formula that we discussed before, but it also just uses our intuition about what we're really taking, what we're really computing with this integral. We're computing the volume of these infinitesimal disks. Okay, so for us that means it goes from -2 to 2, because that's where the parabola hits the x-axis, and we're looking at pi times 4 minus x squared dx. Okay, we can pull that pi out, -2 to 2. 4 minus x squared, we'll FOIL that out, and we'll get 16 minus 8x squared plus x to the 4th dx, which gives us pi times 16x minus 8/3 x cubed plus x to the 5th over 5, evaluated from -2 to 2. Simplifying further, we get pi times, and you know what, one way to simplify this even further is to observe, I could have just as easily cut this in half at x equals 0, right? So let's say I cut this in half with a big red plane. Okay, and now I'm only looking at the right half. So then I could just as easily call this 2 pi times this same thing, 16x minus 8/3 x cubed plus x to the 5th over 5, from 0 to 2. Okay, again, because we're just taking the volume on the right half of the right half and then multiplying by 2. And now we can plug in our values. Note that all of the values at the endpoint 0 are going to vanish, so we can just focus on the endpoint 2. 32 minus 64/3 plus 32/5. Okay, and if you'd like, you can simplify that, but this is fine for now. Okay, so that was the method of disks. Actually, before we move on, I just wanted to go back to that this rendering software, and if instead of looking at this surface, we look at what we're thinking about when we approximate by disks. So what we're doing is we're saying, let's assume a constant radius, so we have a cylinder that's approximating the curve, and then what we get when we rotate and get these constant cylinders looks something like this. And what we're doing is we're trying to approximate this green volume using these blue disks. So you might say that doesn't look like a very good approximation. But if instead of these kind of bigger steps, we use smaller steps, okay, so now these are thinner cylinders, but a closer approximation to the curve. Then we get these smaller disks. We can turn this a bit so you can see what this looks like from different angles. And this is a much better approximation to this green surface. Okay. So that's what we're doing when we use the method of disks. We're trying to approximate that volume using these cylinders. Okay, but now we're going to use the method of washers, where the region is not touching the axis of rotation. So what happens looks kind of like this. You've got some region here, some axis of rotation here, and when you spin it around, you get these holes. Right? There's a hole here representing the empty space between the region and the axis of rotation. Okay, so yeah, this picture might not give the best image of it, but you get the idea. We're representing something that has a hole in the middle. And that's why we talk about washers. This thing is a washer. And whenever we have the cross sections given by washers, we use the following formula for its volume. The infinitesimal volume dV of H. Okay, so we're looking at the infinitesimal volume of a washer at position H is given by the cross-sectional area of the big disk. So if you imagine this part as a disk that's completely solid, minus this part. So you take out the hole. You compute the entire thing, and then you take out the hole in the middle. And that's given by pi times big R of H squared minus little r of H squared dH, where big R is the outer radius at position H, little r is the inner radius at position H, i.e. the radius of the hole, and dH is the infinitesimal thickness along the line of rotation. Okay? And here we get a more explicit formula when we're rotating around the x-axis. So if the region is bounded by y equals f outer, and that's above, and y equals f inner below, from x min to x max, then this is our formula for the infinitesimal volume, and the total volume is obtained from the integral from x min to x max of pi times f outer squared minus f inner squared dx. Okay, and let's just draw a quick picture to represent what's going on here. So we have f outer and f inner, and these are being rotated around this axis of rotation. So you can think about what happens here as, think about this tiny rectangle as you rotate it around. You get a shape that looks like the washer, whose infinitesimal volume is given by this formula. Okay? And just as we did with the disk version, with washers, we also have a special formula for rotating around the y-axis. If the region is bounded by x equals g outer above and x equals g inner below, from y min to y max, then the infinitesimal volume is given by the formula below, and the total volume will be given by integrating from y min to y max of pi times g outer squared minus g inner squared dy. Okay, and just to give a picture of that. So here's our axes, and let's say we have g outer and g inner. Okay, g outer is always further away from the axis of rotation, and g inner here. Then when we do this rotation, our cross-sectional area looks like this. Again, nice washer. Whose infinitesimal volume is given by this formula. And if you, all the way across, and if you want to get the area of the full region here, the volume of the full region, then you use this formula. Although I think I don't think I appropriately represented this as a reflection, but hopefully you get the idea. It'll be a nice solid where you have some thickness in the walls, but it's got a tunnel through it, so it looks a lot like a donut. Okay, so let's look at an example. Let R be the region bounded by x equals y squared and the line y equals x. Compute the volume of the solid obtained by revolving R around the y-axis. So as we always do with these problems, first thing we have to do is draw the region. Okay, so here's our axes. We have x equals y squared. Okay, so y equals x squared is a parabola pointing up, so x equals y squared is a parabola pointing to the right. So let's draw that. Okay, that's x equals y squared. The line y equals x, that we're familiar with. It hits here and here. Okay, this is x equals 1 and y equals 1. Okay, so here's our region. And we're going to be rotating this around the y-axis. So it looks like this. Okay, you reflect the region across the y-axis, and then you can draw circles to show how things connect. Okay, so looks in this case, because the region hits the axis of rotation, it's not going to be solid all the way. It's not going to be a tunnel all the way through. It's going to look kind of like an ice cream cone with some thicker walls. Okay, so now let's try and figure out how to apply the method of washers to compute this volume. So let's get a cross-sectional area. Yeah. So it looks something like this. This is our washer. So thinking about the y-axis as the axis of rotation, the outer radius is given by the thing that's further out, obviously, and the inner one is the thing that's closer to the axis of rotation. So in our case, this is going to be given by the line x equals y, is the outer one. And the inner one is the curve x equals y squared. Okay, as for the infinitesimal thickness, because we're moving from the bottom to in a positive y direction, our infinitesimal thickness is dy. Okay, so now writing this all up, we're looking for from x min to x max. Okay, so that's from 0 to, x min, I should say y min, because we're integrating over y, since we're moving from a small y to a large y. So we have y min equals 0, and y max equals 1. And we're integrating pi times g outer. So in terms of y, this is going to be x. Sorry, in terms of y, this is just given by y. That's squared minus g inner squared, which is y squared squared dy. Okay, and from here it's relatively simple. Pi integral from 0 to 1, y squared minus y to the 4th dy equals pi times y cubed over 3 minus y to the 5th over 5 from 0 to 1, which gives us pi times 1/3 minus 1/5, or 2 pi over 15. Okay, and that is the volume of this ice cream cone. Okay, and we just got that from applying the method of washers, thinking about what each of these cross-sectional washers looks like. Okay, and a general strategy for disks and washers. First, draw your region, understand where your region is relative to x-axis or y-axis. Then you identify the axis of rotation. Am I going to be rotating, around the x-axis, around the y-axis, maybe around another line? draw an example cross-section of the solid of revolution. So that's what we did here with this red washer that I drew in the middle here, to understand how I can express the infinitesimal volume to take the integral, label the functions defining the radius for disks or the inner and outer radii for washers, and then set up the volume integral using the labeled diagram. And that's a good strategy in general to take you all the way through, but like with many of these types of problems, it's all about getting a good amount of practice with all sorts of different problems. Okay, best of luck.